Before diving into the different properties for log functions, we want to start off with a review of log functions in general, which are functions of the form y equals the log base a of x. And keep in mind that statement is the same thing as saying a to the y power is equal to x, which is the inverse of a to the x equals y. So essentially what we have are exponential functions and log functions, which are inverses of each other. The same properties apply still for a. A has to be greater than 0, and a cannot be equal to 1. In the graph on the left, we have the case where a is greater than 1. We have an exponential function, in this case specifically y equals 2 to the x, and a log function, y equals log base 2 of x. And those two functions are symmetric about the line y equals x, as any two inverse functions are. On the right, we have the graph of y equals the log base 1/2 of x, and y equals 1/2 to the x power. So we have the case where a is somewhere between 0 and 1. In both cases, we can see that the domain for our log function is going to be from 0 to infinity, and our range will be from -infinity to infinity. The domain has an open bound at 0, that open parenthesis, because what we have occurring in either case, regardless of our value for a, is a vertical asymptote at x equals 0. In the first case, where a is greater than 1, we see that our function is increasing on 0 to infinity. And in the second case, where a is less between 0 and 1, we have a decreasing function. So whether we're talking about exponential functions or log functions, that value for a determines whether it's increasing or decreasing. And it's the relationship between exponential and log functions that's critically important to get sort of locked into your brain to continue to work with these problems. So again, if we have y equals the log base a of x, that's true if and only if a to the y power is equal to x. These two statements are interchangeable, meaning we can take any given exponential statement and rewrite it as a log. In this case, if we have 81 equals 3 to the 4th power, that means we have our value for a, which would be 3, raised to our value for y, which would be 4, equal to 81, which is our value for x. So we can take this and translate it back into log form to rewrite it as 4 is equal to the log base 3 of 81. In example 2, we have e to the x power is equal to 11. Again, if we think of this as following that same format as a to the y power is equal to x, that means we can translate this into log form as x equals the log base e of 11. In this case, we have one more step we can apply just to simplify our notation a little bit, and we can rewrite this as x equals ln, which is short for the natural log of 11. So anytime we have a log base e, we have what we refer to as the natural log. And that natural log occurs frequently enough in mathematics that we give it its own special notation, ln. So just as a shorthand notation rather than writing out log base e in every scenario. We can also take a log function and translate it into an exponential. What we do is take whatever the base of that log is, so in this case it's base 8, raised to the exponent on the other side, set equal to 64. In example 4, we have ln of 2, which again is the log base e of 2. is equal to x. So we can take that base of e raised to the value on the opposite side of the equation, set equal to 2, and we've translated that log statement into an exponential statement.